Yes, me friend, them set me free again. Yes, me friend, me did.
Okay, today we're still continuing on with logarithms. This topic takes some time to absorb. And it was nice to start out with a little Bob Marley to sort of get us in the right mood. Okay. What I want to do is I came up with a problem that I want us to address, a few items related to logs to see if we can sort of cement into your brain what a logarithm is and how you can have a feeling for it, because that's kind of a new topic for everyone. And then after we're done with that, I want to make sure we start solving some actual equations. You've been solving equations since you started algebra, linear equations, quadratic equations, polynomial and radical equations. And now we're transcending algebraic processes and moving into what an area called transcendental functions, which are transcendental functions are exponential functions, logarithm functions. They transcend algebraic processes. And there's some other stuff after this course in trigonometry, which are also transcendental functions, different types of things. So we then want to start being able to solve some equations of these type. And then once we understand the fundamentals of how to do that, we want to start actually working on some applications. And I mentioned earlier in the course that this topic, exponential functions and logarithms, are widely used in many different branches of science and business and finance. So probably more so than a lot of the algebra that you've already learned. Okay, so let's start with this question over here, where what I want us to do is to see if we, first of all, numerically can look at these four logarithms and have a sense of what kind of value they should each have. And then we want to write an inequality. We want to order them from smallest to largest, left to right, as an inequality, smallest to largest. So, first of all, let's go back to previous session where we talked about what is a logarithm. And I asked you previously, if you were trying to explain this to somebody that had never even heard of the word before, how you would explain it. One way of explaining to somebody what a logarithm is it's an exponent. Okay, everybody got that? We talked about that before. It's an exponent. So, what we're looking at right here, where we see a logarithm base 3, somebody want to suggest how they might numerically think about this in terms of numbers? Yes?
Would it also be 10 to the third power?
No. It's kind of like you have to almost talk your way through it as a sentence. What's the exponent of 3 that yields 10? Just kind of read it like a sentence. What's the exponent of 3 that gives you 10? If you wanted to write it down as a question, if I wrote this with a question mark right here, I could write an equivalent statement that would be what? What would be an equivalent? If I call this my unknown symbol here, what would be another way of writing this sentence? This is a complete sentence. 3 to the... 3 to the question mark, because the logarithm is an exponent. That means this question mark is the exponent. This is the base. 3 to what power gives you 10? If you think of it that way, you can have a mental estimate of this value.
Isn't the value 10?
Well, no, this is a number. This is going to, each of these four items here are numbers. Each of the four items are numbers. What this number is going to be is the exponent of 3 that gives you 10. Think about it. Anybody want to offer a suggestion that's close?
About a little more than 2.
A little more than 2.
A little more than 2. If it was 2, 3 to the 2 would be 9. That would be too low.
But 3 is too high.
And 3 raised to the 3 power, 3 to the 3 power would be 27, way too high. We're trying to get a number trapped in between here, one that is just right. Somewhere between 2 and 3, probably closer to
2.1.
3 to the what?
1/3.
Hold it. 3 to the 2 is 9. We're trying to get a result,
It's
Tyler.
going to be much closer to 2 than 3.
I mean 2.
Thank you. Okay, good, Tyler. Okay, the number slightly bigger than 2. Number slightly bigger than 2. This is really important. Trust me. Okay. We need a number. This result here is going to be a little bigger than 2. This way of thinking of it. Because when you see one of these crazy things, you don't want to just grab your calculator and blindly believe what it tells you. Matter of fact, your calculator does not have a log base 3 button. So you're stuck. Okay. So, what's the exponent of 3 that gives you 10? It's going to be a number a little bigger than 2. Everybody feel good about that? Okay. Now, use your own brain. Let's see you go too low, too high, and then your question mark is going to be right in between there somewhere. See if you can write down your low value, the value that would be easy above it, for the exponent of 2. The exponent of 2 that's going to give you a number close to 9. Do the same thing here. I gave you that handout, and I've essentially, which is what is written up here on the board. A couple of you came in late. Would you come grab one? So back here now, what you, I hope, are thinking, somebody want to tell me? How would you say it? Ariel, you want to help me? 2 to the x, or 2 to what power? What's the exponent of 2 that gives you 9? Now, what would be a little bit low?
3.
3 would be a little low, wouldn't it? Because 2 to the 3 power, you know, is 8. And 2 to the 4th power would be 16, way too high. So you're probably going to estimate a number like what? A touch bigger than 3. Remember what our objective is. Take these 4 items here, these 4 logarithms, and make an inequality from smallest to largest. Okay? This, if you can do this, you're going to be in really good shape as far as handling logarithms goes. So we should expect an answer to be a touch bigger than 3. Feel good? And over here, now, something I had not mentioned yet in previous sessions, very important. If you see the word log written with no base shown down here, it's called a what kind of logarithm? If you've been reading the book, it's called a common logarithm. Use it a lot in chemistry. You can use it a lot in business. Common log. This is called a common logarithm, and the base is what? The base is 10. Understood. The base is 10. So 10 to the 0 is 1, and 10 to the 1 is, I'm sorry, 10 to the 0, 10, base is 10 here, understood to be 10. 10 to the 0 is 1, 10 to the 1 is 10, and that's close. So the number is going to be probably closer to what, 0 or 1? It's going to be near 1, but slightly less than 1. Notice how I use these little exponents, these superscripts, to indicate a little bigger or a little less than a certain value. If you get in the habit of doing this in math, as you move further along in applying math in courses or out in the world, you'll have a real good sense of what kind of results you should end up with before you punch your darn calculator. Okay. Finally, over here, ln, that means log base e. This is log base e. right? And they're called natural logs, natural logarithms,
Why is that one natural?
because of something I haven't talked about yet. It shows up in nature, and I'll give you a real short, sort of quick explanation. There's a much more detail to it. Let me go ahead and do that right now. If you look out in the galaxy with a telescope and you see spiral nebulae, okay, they spiral out. If you take a shell of nautilus and you slice through it, the air chambers in it are in a spiral form. Those are things that occur in nature. If you would model that curve, that spiraling curve, with mathematics, the base of that spiral is a base E exponential. It's a base E exponential. There's a very important also feature or characteristic of E that we have to just kind of wait until you start calculus to really understand what it is. It's very important. I don't think I'm going to talk about it this term. Possibly in trigonometry or in first term calculus. Definitely in first term calculus you'll learn about it. Okay. So that's why they're called natural logs, is because the modeling that occurs oftentimes fits things that occur in nature. Okay. So this is a log base E. They're also called Napier logarithms in some books because of Napier, who did a lot of the early work with logarithms. So what we're looking for here is what? How would you explain it to somebody?
Exponent of E
The exponent of E
that equals 3.
that gives you 3. Now E is what kind of number? What's the value? Good. 2.718 approximately. So keep in mind that E is about 2.718. So we're looking for the exponent of E that gives us a number near 3. So 1, E to the 1 would be just a little bit low, wouldn't it? E to the 2 is up over 7. I think it's around 7.4. That'd be E squared, E to the 2 power. Okay, that's way too high. So I have to be expecting a number a little bigger than 1 here. Can you folks do that? If I gave you several logarithms, you should be able to do that on your own. Okay? So now, once you have that mental thinking down, we can now order these smaller to larger. The smallest one of the 4 you see is log of 8. Log of 8 is less than the next one, a number a little bigger than 1, the natural log of 3, which is then less than a number a little bigger than 2, this one, log base 3 of 10. And finally, the biggest one is log base 2 of 9. So there is your answer, smallest to largest as an inequality. Okay. Would that show up on the video for people watching the DVD? Okay, good. Now, what you can do is take that sheet of paper now and open it up. The scratch paper I gave you. I folded the paper in half for you. And what I want to do is put up here on the overhead, I'm going to zoom in here. See if I can get that. Would that be readable on a DVD, that image? Okay, thanks. Just checking with the control room. So what I did here is as you can see, I graphed each logarithm. Now remember what logarithms do. Notice they all have vertical asymptotes. What's the equation of their vertical asymptotes, folks? Vertical asymptotes.
Y equals 0.
Not y equals x. X equals 0. X equals 0. Okay? And then their domain, you can see, is all numbers greater than 0. All numbers greater than 0. So, look at the first one up here, log base 3 of x. You're going to, the log base 3 of 1 What's the exponent of 3 that gives you 1? Is 0. You move out to the basis value of a logarithm to see an altitude or a height of 1. A height of 1. Look at the other one over here. Look at the log base 2 of x. Here you only have to come out to x equals 2 to see a height of 1. Look at this one down here, the base 10 graph, the common log. You have to come clear out to 10 to be up to 1. Try to get this idea into your head. Very, very important. And then look at the natural logarithm, the base e logarithm, where you have to be out to e's value to be up to a value of 1. So graphically interpreting the question that was originally asked, if we were looking for the log base 3 of 10, here it is. It's out here. 9 is too low. It's only a height of 2. Just past it is the log base 3 of 10, and the height is a little bigger than 2. Look at these other graphs. Log base 2 of 8 happens to be exactly 3. What's the exponent of 2 that gives you 8? The height would be 3. And the log base 2 of 9 is the number a touch bigger than 3. You can see it right there. And then the last two, the log base, the common log of 8 has to be a little less than 1. You can see its height right there. And finally, the last one, the natural log of 3. The natural log of 3 is a value just to the right of e here where 3 is, and the height is a little bigger than 1. Okay. What we did is we looked at the numerics, the numeric characteristic of these things, and then we looked at the graphics, how it relates to the graphics.
Yes, me friend.